All right, so greetings and welcome to the second exciting edition of 15.18.213 and 15.5.13. Today, we get to talk about bits, bytes, and integers. All right. I know this is going to shock and amaze everyone in the class. You probably never, ever heard this before. Okay? Computers work in binary. Look, I can step past things. I'm very good at this. This is actually a little trickier because there's no table here, but I can even do that one. It's going to amaze everybody, okay? Computers work in binary. They don't actually use decimal, right? You've all seen the T-shirts, right? That, 1, 0, the number 2, right? There are 1, 0 types of people, those who understand binary, those who don't. So here's my question for you, right? Why do computers work in binary? What's that?
Transistors only have 2 states.
Transistors only have 2 states. Is that true?
Basically, it's supposed to count the X state.
How does an amplifier work?
Transistors and other components.
Push-pull amplifier?
I think it.
You do digital logic, indeed. So if you do digital logic, transistors just switch. Okay. Hypothesizing that transistors actually can be used for analog applications also, which I think would be a verifiable hypothesis. What's that? I mean, admittedly, there's a gate current that controls whether it's on or off, but there's an amplification or a gain that's associated with that. That's variable. So at any rate, why? Why is it? I mean, well before there were digital computers, there were analog computers. Yes?
It's easier for the computer to distinguish between a high voltage and a low voltage than a wide range.
Yeah, it's easier to distinguish between on and off than on, 1/3, 2/3, 3/4, 7/8, whatever, and off, right? I mean, here's the example I like to use. And it was much easier when we had normal light switches in the room. But, details. Right now, are the lights on or off?
Yes.
Are the lights on? Yes. And now? Off. Okay, so if we call this 0 and this 1, come on. What is that?
1.
Is that 10% or 20% or 30% or 40%? 50%? What do you think?
1.
No, I mean, really, what percentage brightness is it?
I think 75. I don't know.
You think maybe 75%? What do you think?
40.
40? 80? Help me out. 60, ma'am? 70, right. We can't tell. 40, 60, 80, 20, 70. It's harder, right? It's much easier to distinguish between on and off. And that's why we have digital logic. If I have some signal, right, it's much easier to tell on from off than it is somewhere in between. Now add to that the fact that we never have pure signal. We have signal and noise, right? And so I might take a signal that's exactly 5 volts. Really, it's exactly 5 volts plus or minus some tolerance, right? And now if I go to transfer that signal, some of it leaves, right? We lose some. And the wire acts as an antenna, and we gain some. So our noise signal is whatever we gain and whatever we lose, right? So it's really hard to have anything exact when you have things that are analog. You can't copy things, right? Back in the day, right, when music was stored on tape, right, and you would copy things, it was like a photocopier. Every copy got a little worse because you introduced more noise and lost more signal. There was no way to get it back. Okay. The good thing about a digital signal is that if we say, look, this is on, this is off. We tolerate that in terms of noise. We tolerate that in terms of noise. If we're anywhere here, we can always reset it to fully on, or to fully off. If we're anywhere here, we can always reset it to fully on. And if we ever land in this space, that's the error state. We've lost too much to know for sure. Okay? So with digital signals, we can easily sample to tell what we have, a 1 or a 0, and we can keep that going forever. Not like analog, where it's very hard to tell exactly what we have, and where it only degenerates. Okay. It's unsurprising and unamazing to most of you that binary, as you guys seem to get, right, has two states on and off. And then our numbering system is based upon that. So we have two digits, 0 and 1. So we have the 2 to the 0's place, that's the 1's place. The 2 to the 1's place, that's the 2's place. The 2 squared place, that's the 4's place. 2 cubes place, that's the 8's place. 16's place, 32's place, 64's place, 128's place, 256's place, 512's place, and so on, right? It works just like math did in kindergarten, right? We used the 1's place, the 10's place, the 100's place, the 1000's place, right? You used to rearrange these little things. The unit that was a little square, right? The line that was 10, right? The tens block that was 10 tens into a big square. The cube, right? That was 10 of those things stacked on top of each other for 1,000 or 100. Or no, it was 10, tens, 1,000, yes. So we had the ones, tens, hundreds, thousands. You didn't get past thousands in kindergarten. And so it's the same way, right? We have the ones place, the twos place, the fours place, the eight's place. That is to say 2 to the 0, 2 to the 1, 2 squared, 2 to the third. Just like 10 to the 0, 10 to the first, 10 to the second, 10 to the third, 10 to the fourth, and so on. And that's that. Binary is really tough for people to deal with because it takes so many digits to represent something, right? It's just a pain if you've got to deal with it. So when programmers are dealing with binary but want a more compressed representation, we oftentimes turn to hexadecimal. Hexadecimal is a base 16 numbering system. 1, 16, 256, and so on, right? 16 to the 0, 16 to the 1, 16 to the 2, 16 to the 3, 16 to the 4, 16 to the 5, 16 to the 6. Right, blah, 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 blah. The good thing about it is it's a power of 2 system. So every 4 binary digits can be represented as a single hex digit. That's really nice because I have these groupings of 4. Okay? And if I want to know what bits, what bit 10 is, I only have to, decode one of those groupings. Right? It's very easy. Decimal is much harder, right? Because decimal is not a power of 2. Okay, so you can't tightly group the bits. Okay. There's no way of just taking a group of powers of 2 and having it, densely represent a power of 10. Right? If I take these 2 bits, I have 0, right, through 3. If I take these 3 bits, I have 0 through 7. Right? 7 is less than 10. If I take these 4 bits, I have 0 through 15. 15 is more than 10. I don't have exactly 10. Right? Whereas if I take a group of 4 bits, I have 0 through 15. That's exactly 16 digits. Okay. So people, use commonly the decimal numbering system because it's convenient for us. It's not just because we have 10 fingers and 10 toes and whatnot, right? Although we like to say that. It's because it's for common purposes and easy for us to wrap our brains around having 10 digits. We don't need a big lookup table to see what some digit means. Okay. So the logical things for us to use are power of 8, octal, or power of 16, hexadecimal, to represent binary. They're very close to what we commonly use as a power of 10, but they're powers of 2, so it breaks up nicely. Sometimes programmers do use octal, but as it turns out, our brains don't state explode at 16. 16 is still very comfortable for us. And so most of the time, programmers will use hexadecimal. You could imagine a numbering system that had 32 characters. Okay? Most of the alphabet plus 0 through 9. Okay? But at a certain point, it would get really hard to remember, like, what exactly is J? Just more state than we're used to dealing with. Data representations. When we deal with programs and we deal with data types, the data types are ultimately represented in binary. Okay? A character tends to be 1 byte, 8 bits. A short tends to be 2 bytes, 16 bits. Int, 4 bytes. Sorry, int 4 bytes, 16 bits. Short, 2 bytes, 8 bits. Long, right? On most systems, it's still 4 bits. Except on 64-bit systems, right, the current generation. Man, I'm having trouble with math today. On most systems, a long is still 4 bits. Okay? 4 bytes, 32 bits. On the 64-bit systems, it actually is now larger. It is 64 bits. Okay? Longs, 64 bits across all systems. Floats, 4 bits across all systems. Doubles, 8 bits across all systems. A long double, it's 8 bits on most older architecture 32-bit machines. On Intel, it's a weird 10 or 12 bits, and we'll talk about why, on 32-bit systems, and 10 or 16 bits on 64-bit systems. Why 10, 10 or 12 or 10 or 16? It has to do with the native format on the Intel processor, or using the standard IEEE format that the processor also supports. Pointers, okay. Memory is addressed, right, basically with an index into it. Byte 0, byte 1, byte 2, byte 3, byte 4. So memory is addressed with an integer, basically. Okay. So pointers are going to be, 4 bytes. Okay. 32 bits on 32-bit systems, or 8 bytes, 64 bits on 64-bit systems. What does it mean we say we have a 64-bit system? That means the register size is 64 bits. The size of the data path is 64 bits. The basic size of data that the system deals with easily is 64 bits. What happens if it has smaller data? That's okay. It just doesn't use all those bits. What happens if it has larger data? Well, that's okay, but it might take 2 paths, 2 trips to move the thing. Or in the case of floating point numbers, that it's using sort of a separate part of the processor. So what to say? We've all heard about Boolean logic, logic involving true and false. Right? You probably took some logic class over in philosophy that dealt with this, or played with it a little bit in high school. But the basic idea is that we deal with ors and ands and exclusive ors and things like that. An and condition is only true if both of the constituent states are true. You can eat dinner if you have a fork and a knife. Okay? You can't cut your food with one or the other. Okay? And that's a logical and. And so it's only true if both conditions are true. Otherwise, it's false. You can leave the class when the class is over or the fire alarm rings. So you leave if class ends, or if the fire alarm rings, or if the fire alarm rings when class ends. Okay. The not operation is opposite day. You played this game as a kid. Everything that's true is false, everything that's false is true. So if I negate something, I take it from a false to a true or a true to a false, from a 0 to a 1 or a 1 to a 0. An exclusive OR is like an OR condition, except for this state here. When they're both true, it's actually false. Okay? So, this is like when you were a little kid and, your father said, well, you can have an ice cream sandwich or a cookie. What your father meant is you could have one or the other, but not both. If your father was a computer scientist, your father might have said, you can exclusive OR, right? Put that cell phone away. Okay. Right? So exclusive OR is true, one or the other, but not both. Okay. And so these form the basis for these logical operations, form the basis for a lot of decision making in binary systems. And here you can see we're applying the bitwise operators and, or, exclusive or, and not to two inputs in binary. And the operator is applied to corresponding bits in both of the operands. 1 and 1 is 1. 0 and 0 is 0. Okay? And so we see we only have a 1 when both columns are 1. It's the AND operator. Here, you can see we're going to have a 1 anytime we have a 1 in any column, in either column. The only time it's 0 is when both columns are 0. That's the OR operator. The exclusive OR operator is going to be true only when there's a 1 in exactly one of the two corresponding places. Not if they're both 0, not if they're both 1. 1, 0, 0, 1. Okay, boom, boom. 1, 0, 0, 1. 0 there, 0 there. Okay, and not negate, just opposite day. Okay. We refer to the width of a number as how many digits there are. So if we say the width of an integer in this particular system is 16 bits, we mean there are 16 binary digits. Okay. Now, sometimes we use integers not really to count things, okay, but just as bit sets, where each bit represents something different. Like, let's say I wanted to take attendance. I could say you're going to be represented by bit 0, and you're going to be represented by bit 1, and you're going to be represented by bit 2, and you're going to be represented by bit 3, and your bit is 4, and your bit is 5, and your bit is 6, and your bit is 7, and your bit is 8, and your bit is 9, and your bit is 10, and so on. And if you show up to class, we flip your bit on. If you don't, we flip your bit off. Now I have an integer acting as a bit set. That's to say it's acting as a set. It tests membership. In the set or not in the set. If the bit is on, you're in the set. If your bit is off, you're not in the set. You weren't there. Okay? So now what? Well, now I can pound define a particular position to be yours. So let's say you're bit 3. I'll have some pound define. What's your name?
Josh.
Josh. That'll say pound define Josh to be 1 left shifted by 3. Now that's your bit. And now I can do an OR to set your bit. Attendance equals attendance or Josh. Bitwise OR. And that flips your bit on, keeping all the bits the same. I can ask if you were there. Right? How would I find out if you were there?
You could just take the and the bits on there.
Take the and. Josh present equals attendance and Josh. Because all the rest of the bits of Josh are 0, except for the one bit that represents you. And if that's also true in the attendance set, then the result will be non-zero or true. We agree? So that's what this slide is talking about. Okay. Now what? Okay. A little more story about bitwise operations. And you can walk through those by hand if you like. Keep in mind the distinction between bitwise operations, okay, and the logical operations, right? Notice 2 ampersand signs versus 1. Notice 2 pipes versus 1. That's a key difference, okay? Because these are the logical operations. These don't look at the individual bits. These look at the integer as a whole and ask the question, is it 0 or not? If it's 0, it's false. If it's not, as a whole, it's true. Okay? And so now what we do is we perform logical operations, but on the whole thing. We take the whole integer and view it as true or false. If all the bits are 0, it's false. If any bit is 1, it's true. And now we perform the operation. That's the difference between the 2 ampersands and 2 pipes and and the bang. 2 ampersands is the logical, dealing with the whole thing as 1. 2 pipes, the bang versus the tilde. Okay, this takes the whole thing. As opposed to a single ampersand, a single pipe, or a single bang, which does the bitwise operations. Okay? So you can go ahead and close your laptop. Excellent, thank you. It's very suspicious when you quit taking notes as the instructor walks by. Might lead the instructor to believe the laptop's being used for social media. Okay. We have some more examples that you guys can walk through in your own time there. This is sort of an interesting one that I do want to pause and talk about, though. P and star P. That's a very, very common construct for pointers. Because referencing a null pointer is bad, right? If you reference a null pointer, what happens? Seg faults. Right? If the pointer's value is 0, it's a null pointer, it's not a valid address. You dereference that, and you get a seg fault. Okay? So if we look at this, P, when an operand to an ampersand operation, is going to be evaluated as true or false. If it's a null pointer, it's false. If it's not, it's true. C uses what's called short circuit evaluation, meaning it doesn't evaluate any more of a logical expression than it needs to know the result. If P is false, is there any way this expression can be true? No, because false and anything is false, right? So C stops there, never looking to see what star P is. Since it never dereferences star P, you never get the seg fault. Does that make sense? So this value is going to be 0 or false if P is null. Otherwise, it's going to be whatever P, the value of whatever P points to. Yes?
How would this exactly be useful to us? Because we're not getting the value that's stored in P. We're getting 1 if it's non-zero.
So, right. So this is checking to see if P is false or if the value is 0, right?
Yeah.
As opposed to if I would do just this, if star P.
Yeah.
Okay? Then it would blow up if P was null. So if I want to take something, if I want to borrow a car, there's a problem if my car count is 0.
Yeah. But why can't we just do if P then star P?
You can do if P then star P. That is perfectly valid C. Most people would prefer this construct because it's shorter. But it's, you can do it with an if statement just the same. Yes.
It doesn't matter what P is storing, right? It'll still get you the value of P.
Well, so look at this expression. This expression is going to be a true or false expression because that's the result of an ampersand operator. So basically, it's like looking at star P as a true or false value, okay? But we're checking to make sure that it's valid before we do. Does that make sense?
Yeah.
So it forces it to false in the case where it would otherwise be invalid. Okay. Left shift and right shift. Left arrow 3. That says take whatever bit pattern we have and shoves 3 zeros to the right of it, in effect pushing it to the left. Okay. Given that all data types we saw have a fixed width, if I shift things inside to the left, okay, the stuff on the left is just going to disappear. It's going to fall off the other side. It's called a left shift. Okay. When it comes to a right shift, we're going to have 2 different types of right shift. A logical right shift is exactly the same. We shove some bits on the right, we shove some bits on the left, pushing everything to the right. If I shove in 1 bit on the left, 1 bit's going to fall off the right side. Okay. So in the common case, a left shift has the effect of multiplying by a power of 2. If I left shift by 1, the thing in the 1 position becomes a 2. The thing in the 2 position becomes a 4. The thing in the 4 position becomes an 8. So it has the effect of left shifting, of multiplying by 2, right, for every time I left shift. Until the point where I start losing precision at the left-hand side. A right shift, therefore, has the effect of dividing by 2. Okay. Obviously, truncating as things only fall off. It doesn't round up. Okay. But as we'll learn about shortly, there's another number representation, okay, called 2's complement. And with 2's complement, when we talk about it, you'll learn that it's really important to preserve the left side bit. If the left side bit is a 1, it's really important to keep it a 1. And if the leftmost bit starts out as a 0, it's really important to keep it a 0. And we'll talk about why soon, okay, meaning today. An arithmetic right shift respects that. So if the high bit is a 1, it inserts 1s. If the high bit is a 0, it inserts 0s. Okay? A logical right shift doesn't. It always inserts 0s. Okay? And again, when we talk about 2's complement in just a few minutes, we'll talk about why that is. Okay? If you shift by more or less than the words, by less than 0, right, that's undefined. In other words, the C standard says that if you try to shift by a negative number, there's no guarantee that's equivalent to a right shift. Right? If I left shift by -5, that's not necessarily the same as right shifting by 5. The result is undefined. Similarly, if I have a 32-bit type and shift all my bits out, there's no guarantee that I'm left with 0s. Okay? The result of that is undefined. The reason for this is that part of the philosophy of C was that the operations, the basic operations in C, should be the same as whatever the basic operations are in the actual hardware. They didn't want to impose new requirements, because a new requirement could mean that one operation in C like this would require multiple operations on the processor. And they wanted to minimize the situations where that was the case, to make these operators really align with the processor operators. And since processors don't necessarily do these things, they didn't make them requirements of the language. Thus, they didn't hide that complexity. Okay, so we see with an original argument of 0, 1, 1, 0, 0, 0, 1, 0, if I left shift by 3, this 1 is moving over 1, 2, 3 positions. Okay? So these 3 positions fall off the edge. These 3 bits come over here. My new 3 bits are over here. If I right shift logical by 2, these 2 positions are going to fall off. That 1, 0 goes away. Everything else shifts to the right, and 2 zeros get put in here. A logical right shift is going to do the same thing in this case because, arithmetic right shift is going to do the same thing in this case because my high order bit is a 0. But if I come down here, where my high order bit is a 1, here I'm shifting 1s in instead of 0s. An arithmetic shift, when you do a right shift, adds in whatever that bit already is. Okay? There is no such thing as an arithmetic left shift. You always put 0s in on a left shift. The logical and arithmetic turn out to be the same. We'll talk about why shortly. Do you have a question or just stretching? Okay. Okay. Ha! I knew I should have looked at these slides before class. They put math on my slides. And that funny E thing. Yes?
At the bottom on the previous slide, you had undefined behavior. Why can't you shift by the word size?
Well, if you shift by the word size, the expected behavior most humans would have would be that it would be all 0s.
Yeah.
But at the point in time where they were drafting the C standard, there was some processor that didn't do that. That if you tried to shift by more than the word size, it went. Did you guys get that on tape? You sure they got it?
Yeah.
Okay. No, just kidding. Okay. And so they didn't make it a requirement because they didn't want a situation where the processor had a shift operation, yet the C operation that corresponded to that had to do a shift and then an assignment. Whose question was that? Does that answer your question? Okay. And then once they did that, they wanted to carry that behavior forward because they wanted the new compilers to be backward compatible with the old source. And so that's where we are. Okay. Oh, God. This is terrible. I've got the funny E Riemann something and subscripts and superscripts. Man. Exponents? I think we learned in 3rd grade that they use a dot instead of an X for math for multiplication sometimes. Okay. This is designed to look academic and complex. It really is very easy. Okay? If you think about a binary number, each digit in a binary number represents a power of 2. 2 to the 0, 2 to the 1, 2 squared, 2 to the 3rd, 2 to the 4th, 2 to the 8th, and so on. 1, 2, 4, 8, 16, 32, 64, 128, blah, blah, blah. That is the value associated with the corresponding bit position. Right? Bit position 0 has a value of 2 to the 0. Bit position 1 has a value of 2 to the 1. Bit position 2, 2 to the 2, 2 squared. Bit position 3, 2 to the 3rd, or 8, and so on. So if I want to know the value of a binary number, all I do is I look at it bit after bit after bit. And I ask, is bit 0, 1? That is to say, is 2 to the 0 present? If it is, I add it to my value. I then move on to bit 1. Is 2 to the 1 present? Is that bit a 1? If so, I add it to my running sum. Is bit 2 present? If so, add 4 to my running sum. Is bit 3 present? If it's 1, I add 8 to my sum. If it's 0, I don't. And that's how I find the value of a binary number. Just like that's how I find the value of a decimal number. Just like in kindergarten, when you took the number of single squares and added it to the number of rows and added it to the number of big squares. 1 unit plus 3 tens plus 4 hundreds plus 3 thousands. Right? That's all this says. Start at bit 0, working your way to the highest bit, the width minus 1. Why the width minus 1? If I have 16 bits, it's 0 through 15 rather than 1 through 16. 2 to the 0. That way we get the 1. And so this basically says, for bit 0 through bit 31, if we're dealing with a 32-bit number, right? Take whether or not that bit is present, whether or not that bit is a 0 or a 1, and multiply it by the value of the bit. 2 to the 0, 1, 2 to the 1, 2, 2 to the squared, 4, 2 to the 3rd, 8. And this is the 1 or 0 that's in that bit position. And that's all it says. Find the value of a binary number by walking from bit 0 through the last bit, adding the value of that position if and only if the corresponding bit is 1. Otherwise, add 0. Does that overly complicated math make sense to everybody? Okay. Now, this is 2's complement. This is the way we represent negative numbers. I'm going to switch over to the chalkboard for a minute here. Let's start counting in binary. 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Everybody agree? Okay. And this is sort of like if I were counting in decimal. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I carry 1, 0. The difference is I end up carrying much sooner here. 0, 1, carry. 1 plus 1 is 0, carry the 1. 1 and 0 is 1, 1. 1 plus 1 is 0, carry the 1. 1 and 1 is 0, carry the 1. 1, 0, 0. Make sense? 1, 0, 0 plus 1 is 1, 0, 1. 1, 0, 1 plus 1 is 1, and 1 is 0, carry the 1. 1 and 0 is 1. 1. 1, 1, 0 plus 1 is 1, 1, 1. 1, 1, 1 plus 1 is 1, and 1 is 0, carry the 1. 1 and 1 is 0, carry the 1. 1 and 1 is 0, carry the 1. We agree? In this example, I'm generating new bits as I need them. But in a processor, I have a certain width, 16 bits, 32 bits, 64 bits. So let's say that I have a 3-bit processor here. I actually have in memory 0, 0, 0, then 0, 0, 1, then 0, 1, 0, then 0, 1, 1, then 1, 0, 0, then 1, 0, 1, then 1, 1, 0, then 1, 1, 1. But when I do this carry, I have a problem. I only have 3 bits. I'm back to 0. Do you see that? I've started over. And now if I add 1, I'm back here, right? Okay. So let me ask you something. If I have x plus y equals 0, what is y? Everybody agree? I have 1, 1, 1 plus y equals 0. What does y equal? What's the obvious simple answer I'm looking for? What did I do over here? Y equaled negative x, right? What am I looking for here? Y equals negative 1, 1, 1, right? Anybody disagree? We all happy? So what did I add?
1.
To 1, 1, 1 to make it 0? 1. Something's wrong. I just found that 1 equals negative 7. How many of you guys remember math class where they showed you that 9 bar actually equals 1? Mike fell. Thank you. How many people remember math class? They showed you like 0.9 bar equals 1. You guys remember that? How many of you believe them? I still don't believe them. I did that proof 1,000 times. Okay. This looks a little weird, doesn't it? According to this, 1, 1, 1 equals negative 1. Do you agree? Okay. Let's go with that for a minute. Let's assume that 1, 1, 1 is equal to negative 1. Okay, what's negative 1 plus 1? Okay, let's add 1. Just for symmetry. Is this working out? Do you guys agree this is working? Okay. Okay. So hypothetically speaking, if 1, 1, 1 is a negative 1, this sort of works, right? Let's play around some more. Let's suggest that I take a number, any number, and I complement it. We agree that those are complements? And I add them together. What do I always get? What's that? All ones, right? Negative 1. We agree? So this would suggest that if I take these two things and add them together, I get negative 1. What happens if I take these things and I add them together and I add 1? What am I going to get every time? Do you agree? If I take a number and complement it, add the two numbers together and add 1, I get all zeros, right? So x plus the complement of x plus 1 is equal to 0. Do we all agree? Therefore, x equals negative the complement of x plus 1. Do we agree? So the complement of x plus 1 equals negative x. Do we agree? So now let's say we base a system of math based upon this, where positive numbers, non-negative numbers, are whatever they are. Negative numbers are their complement plus 1. Well, in theory, if I add 1 to the complement of a number, plus 1, its negative value. If I add 1 to negative 5, should I get closer to or farther away from 0? Closer to, right? If you add a positive number to a negative number, you get closer to 0. At least until you cross 0. Okay. And how much closer should I get if I add 1? Do you believe 1? Okay. So, if this is x, and we know this is negative x, we all agree? I'm sorry. Where's my negative x? My negative x is the complement of this plus 1, right? Okay. So my negative x is going to be the complement of this, 0, 1, 0, 0, 1, plus 1. 1 and 1 is 0, carry a 1. Do we agree? And we just showed that if we add these together, what do we get? 0, 0, carry a 1, 0, carry a 1, 0, carry a 1, 0. That 1 drops off the other end. Okay, all zeros. So now if I add 1 to this, okay, 0, 1, 0, 1, 1. And I add x to negative x plus 1. That's basically what I did, right? What should I get? I should get 1. Okay. So what do I get if I add x to negative x plus 1? Zero and 1 is a 1, right? Everything else is the same. I get my 1. You see that? So this is what we call complement arithmetic. In complement arithmetic, we represent non-negative numbers as we always did before. We represent negative numbers by complementing and adding 1. Why? That makes them the additive inverse. Does that make sense? The only problem we have with this is distinguishing what is in 2's complement representation and what is in normal representation. Because if I give you a number like 10110, you don't know if that's a positive number or a negative number. You don't know if you should subtract 1 and complement it to find its real value, or if you should take it at face value. So here's what we do. We use the highest bit as a sign bit. If the highest bit is a 1, we interpret it as 2's complement. That is to say, if we want to know its value, we subtract 1, negate it, and then make it the negative of the resulting value. If the leading bit is a 0, we leave it alone. This says that we have negative numbers ranging from 1, 0, 0, 0, or whatever, right, to 1, 1, 1, 1. We have non-negative numbers ranging from 0, 0, 0, 0 to 0, 1, 1, 1. Do you agree? If you add 1 to this positive number, the largest positive number, you get 1, 0, 0, 0, which brings you here. That would be the most negative number. Because remember how this works. This is the most negative number, and as we add things to it, we bring it closer to 0. Does that make sense? So in 2's complement arithmetic, the bit pattern 1 followed by all zeros is always the most negative number. The bit pattern 0 followed by all 1s is always the most positive number. Does that make sense? The bit pattern 0 is 0. Do you see why that is the way it is? A lot of people memorize this stuff, okay? And they spend their lifetime trying to memorize this. There's no reason to memorize it. If you think about it, it makes sense. If I know that I'm using this as the sign bit, everything else follows from there. I know this is the most negative number because anything I add to a negative number brings it closer to 0. Okay. I know that this is the most positive number because if I add 1, it wraps around to negative. Does that make sense? On the non-negative side of the number line, we're adding to 0 as we take all zeros and start to add to it. Yeek. On the negative side of the number line, we're starting with the most negative number, 1, 0, 0, 0, and adding to it to bring it back to 0. Where I have 1, 1, 1, 1, plus 1 is 0. 1, 1, 1, 1, we already said always represents what pattern? What's that? Negative 1, right? 1, 1, 1, 1, right? Subtract 1, 1, 1, 1, 0, complement, 0, 0, 0, 1. So you can memorize this, make your brain full, or you can realize why it all works. 1, 1, 1, 1 plus 1 is 0. Anything plus 1 that's 0 is equal to negative 1. Okay? And we go from there. All right? So that's going to be our most negative number, all the way over. Starting with that, adding this back to bring us closer to 0. Okay? All right. Switching back over to the slides. So as we look over on the right side of this, and we see another scary fraction, not fraction, equation, what are we looking at? Well, there's nothing to be scared of here. This looks a lot like this side, right? Here we sum from 0 to width minus 1. Here we sum from 0 to width minus 2. Why width minus 2? That leftmost bit is the sign bit. Whether the number is negative or positive, we're going to be adding the things that aren't the sign bit. Either adding them to 0 or adding them to the most negative number. So we sum up those things. Does that make sense? In the event of a non-negative number, it's 0 plus that sum. In the event of a negative number, it's the most negative number plus that sum. Now we look at that sign bit. The x sub w minus 1 bit, the leftmost bit. If it is a 0, we start with 0 and we add everything from there. So this term is going to be a 0 and we add that. So if this bit is 0, it's negative 0, which is 0, times something, which is still 0. It's 0 plus everything else. If, however, that leftmost bit is 1, it's the most negative number, right? And so we're going to start there and add our way back. So this is going to be 1 times 2 to the w minus 1 times the bit position of that leftmost bit. That's going to give us the most negative number, right? We said the bit pattern 1 and all zeros is always the most negative number. So now it's the most negative number plus all of this, which brings us closer to 0. Does that make sense? We can't quite get to 0 because 0 is going to be the bit patterns all 0. 0 in the high order bit and 0 in all the low order bits. 0 plus 0. Do you see that? What's the value of the most negative number? The sign bit's on, this is all off. What's the value of negative 1? The sign bit's on, and everything else is on. because it's the most negative number plus everything else, which leaves us 1 short of a 0. Make sense? Okay. Okay. Now, is 0 negative or positive? So some mathematicians in the class are trying to answer that question legitimately. With respect to our number line, 0 comes out of the same side of the number line as positive numbers, because it begins with a 0, right? It's direct, not 2's complement. That means that we can represent a number that's more, our most negative number is more negative than our most positive number. Because our non-negative side of the number range goes from 0 to something. Our negative side of the number range goes from -1 to something. They're the same number of bits. So the 0 comes out of the positive side of the number line. Does that make sense? It's the non-negative side of the number line. So my largest, greatest, non-negative number is going to be 1 smaller in its absolute value than my greatest negative number, because the 0 is coming out of that side of the number line. Okay. That's why my most negative number is 1 greater than my most positive number. Do you see that? Don't memorize it. There's tons of this stuff that you can mindlessly memorize, but you don't need to. You just need to keep in mind that it is what it is for a reason. 0 comes out of this side of the number line. It's 0 through something, not 1 through something. Right? This is -1 through -2 to the w minus 1. This is 0 through 2 to the w minus 1 minus 1. Why? I'm starting at 0, so I don't get quite as far. Okay. We talked about the fact that 0 is always 0. We talked about the fact with unsigned numbers, all 1s is my greatest bit pattern. We talked about the other bit patterns that are common, right? All 1s is going to be a -1. A 1 and all 0s is going to be the most negative number. Okay, we talked about why. It's the most negative number plus all the 1s that brings us to a -1. Plus 1, add 1 to a -1, and you see all 1s plus 1 is going to be 0. 1 plus 1 is 0, carry the 1. 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 1 plus 1 is 0, there's nowhere to carry the 1. We throw it away. We're all 0s. So it all works out. You guys see that? Okay. And so, given a particular number of bits, you can figure out what the maximum sizes are. If you do this math, you must be drunk and smart. If you get it right, you must be drunk, smart, and careful, even while drunk. Don't do that, okay? Use the pound defines. All right, if you want to know the maximum size of unsigned long in your system, use u long max. Right? That way, when you compile it on the next generation 128-bit processors 10 years from now, right, it still works. Okay. We talked about these conversion things. These are the functions we looked at before. Here's what's worth seeing. If I take my signed number, and I take my unsigned number, and I take the bit pattern, here I have the bit patterns ranging from 0 to all 1s. For a while, it doesn't matter whether I'm dealing with a signed type or an unsigned type. It's exactly the same. However, once I add 1 to this and I get 1, 0, 0, in the case of an unsigned number, I keep growing. 7 plus 1 is 8, plus 1 is 9, plus 1 is 10. In this case, it suddenly becomes the most negative number. Why? Look at my bit pattern. The most negative number plus nothing. You guys see that? Okay. And then from there, we continue monotonically increasing. Why? We're adding 1. Eventually, here we get to the bit pattern 1, 1, 0. We add 1. It becomes 0. Here we get to negative 1, and we add 0. In either case, it makes sense. Okay. So if we look at 2's complements number line and the unsigned number line, okay, we see that they overlap in a particular range, and then there's this crossover that happens in the higher part of that range, where the most negative number, if you look at it as an unsigned number, is you know, a big unsigned number, right? So if I take a look at my most negative number, that's a 1 with all zeros. Okay? That's going to be immediately above my 2's complement maximum. Why? My 2's complement maximum is 1, 1, 1. One past that is 1, 0, 0, 0. Okay? So if I look at that, here I become negative. 1, 1, 1 becomes 1, 0, 0. Here I'm just adding a 1. 1, 1, 1 becomes 1, 0, 0, 0. Great. I'm not doing anything different without leaving 1. Here I grow monotonically from there, right? Here, okay, what am I doing? I'm adding back and growing this way. In C, if you write a number 2, 3, 4, 5, that number by default is signed. Constants by default are signed in C. If you want them to be unsigned, append a U after them. Okay? Having said that, my default types, like int and long and float, are all signed. If you want them to be unsigned, add the unsigned qualifier. Okay? If there's a mix of signed and unsigned values in the same expression, one variable is a signed type, another variable is an unsigned type, the signed values are cast to an unsigned. So if you have signed plus an unsigned, it automatically takes the signed value, casts it to an unsigned, and then your math proceeds as unsigned arithmetic. Okay. So 0 versus 0 unsigned. Negative 1, okay, a constant. So these are a set of puzzles. And the question is, what's the relationship between these two numbers? 0 signed and 0 unsigned. Well, the answer is they're both equal. What's the relationship between negative 1 and 0? Well, negative 1 is less than 0. Okay. And that's evaluated as signed, right? Because this is signed and this is signed. Negative 1 and 0 unsigned. Well, now I have an unsigned type, so my negative 1 is cast to an unsigned. If I take a negative 1 bit pattern and I interpret it as unsigned, it's a big number, right? It's bigger than 0. Okay? And you can walk through the rest of these as an exercise to the reader. If you have any questions, email the list, ask them at recitation I guess we won't have recitation Monday. Email the list or drop by for office hours. But these are all just puzzles that get at the idea that the first thing you do is, if you have mixed mode, is convert signed values to unsigned values. And then you do the interpretation. The bit pattern is maintained, but it's reinterpreted. It can have the effect of adding or subtracting 2 to the width, right? In other words, if I take a signed number and interpret it as an unsigned number, the higher values are going to become negative values. In the event that I have an expression containing a signed and unsigned integer, the int is cast to unsigned first. Then the arithmetic proceeds as unsigned. Ba-dum-bum. I forgot to ask how far they got in the other section. This is actually 2 days of notes. We'll go for another 5 minutes. We may not align with them exactly. That's okay. This time. Normally we will. All right. So sign extension. If I have a 32-bit number, okay, a 4-byte type, a 4-byte int, and I cast it to a long log, somehow there are more bits. What do I put into those extra high-order bits? Well, if it's an unsigned number, I put in zeros, because I want to add nothing to keep the value the same. If it's a signed number, I want to do sign extension. I want to take that high-order bit and extend it to fill that space. Why? If it's an unsigned number, sorry, if it's a non-negative number, that high-order bit is going to be 0. So by sign extending, I'm adding in zeros. Perfect. But if it's a 1, this is a negative number represented in 2's complement. If I add zeros, it will be interpreted as a non-negative number, right? Because the high-order bit will no longer be a signed bit. So it's clear my high-order bit needs to stay a 1. The good news is, remember how this works. 1 followed by as many zeros as you have is always what? The most negative number. So if I take the most negative number and I add in and I pad the rest of it with 1s, I'm bringing myself back to where I was before, now adding the rest of the bits. Does that make sense? So in the case of a negative number, I sign extend. Because that means all those 1s added together starts out with a much more negative number, but I add a bunch of stuff to it, which gives me exactly what I had before, plus exactly what I had before. So I've done nothing to the value of that number. Does that make sense? If I have a bit pattern all 1s, for example, does it matter if I have 2 1s or 3 1s or 4 1s or 5 1s or 10 1s? What's that? No. What is that value? What's that? -1, -1, right? Always. So if I have the bit pattern all 1s except the last bit is 0, what's that going to be? Yell it out. -2, always. Does that make sense? It doesn't matter how many 1s are there because I'm adding back to the most negative number. If I have more 1s, I'm starting out with a more negative number, but then adding a bunch more to it. Okay. And so here we see a sign extension example. Okay. No magic to this. Okay. I have 15, 2, 13. When I sign extend, the 0 extends to a 0. I have -15, 2, 13. When I sign extend, the 1 expands to more 1s. If I convert from a larger type to a smaller type, it's going to try the reverse of this and simply whack off the high order bits. That works as long as they weren't needed. If, however, they weren't all 1s or weren't all 0s, and I whack off something else, I've changed the value of that number, right? Okay. So, summary. If it's an unsigned number, we add zeros. There's no 2's complement there. If it's a signed number, we do sign extension. That way, if it's a high bit's 0, we add zeros. If the high bit's a 1, it's a 2's complement number, we add 1s. No loss in sign extending. Yes?
When we were talking about the right shifts earlier, you were telling us about how the 1s get shifted to ensure that it stays negative.
Yes.
If we're shifting an unsigned number, does it automatically add zeros, or does it still add the 1s bits?
When you talk about left shifting or right shifting?
Yeah.
So when I right shift, I have to do the sign extension. And you're exactly right. This is why. To make sure that if I have a 2's complement number, I preserve the value.
But what if it's an unsigned number? Does it add zeros or does it add 1s?
So this is an interesting question. If I use the right shift operator, is it an arithmetic or a logical right shift?
On an unsigned one, yeah.
In C, in Java, there are different operators. There's two greater than signs versus 3. In C, there's only one operator. And my memory of the standard actually is that it doesn't require it be anything. Although generally it's interpreted, most modern languages interpret it as an arithmetic shift.
Even for unsigned?
An arithmetic shift, even for unsigned. Let me not tell any lies, let me tell you to try.
Okay.
Because the standard doesn't actually say. But there is a convention seemingly among compiler writers. So give it a try. Then you'll know. Let us know next class. My belief is that it's going to do sign extension in all cases. But let's check me on that. OK. Truncating, it's the same thing. It's basically a mod operation if those leading bits are not all ones for a signed number, not all zeros for an unsigned number, and it actually loses stuff, it keeps the remainder, right? And throws away sort of how many times it spins around. It's modular arithmetic. OK, you can walk through that example on your own. That's a long version of the old same thing we had before. We'll pick up with addition, negation, multiplication, shifting next class. Have a great day, everybody.